All right. Good morning. How are you all? Have a good break? Found it. This is kind of the first time in a long time I haven't traveled for Thanksgiving. It was just a little bit more restful than usual. Today I was going to try to use a fancy new mic. Should have tried a little bit before coming because it doesn't seem to be recognizing it. And my computer decided over the break to update to Windows 11 accidentally. So been I think we're okay, we're live and everything, but there's some technological trouble here for a minute. All right, so last time before the break, we were talking about BOD removal, talking about how to understand what's happening downstream for BOD processes in terms of we discharge some wastewater, when do we have oxygen demand problems, or rather lack of oxygen problems. So I left off saying that we could come back and revisit this problem when we returned. So the beginning of it is, as I drew here, relatively straightforward, not a particularly difficult problem, I don't think. But it's kind of the setup for the slightly more involved problem where we need those new equations. So let's take a minute to kind of refresh our memory here, look at what this problem is asking for, and then we'll move on to the second part. So the wastewater from a previous example has a dissolved oxygen concentration of 2 milligrams per liter and a discharge rate of 1.1 cubic meters per second. River water that's receiving this waste has a DO equal to 8.3 milligrams per liter, a flow rate of 8.7 cubic meters per second, temperature of 20 degrees. Assuming complete and instant mixing, estimate the initial dissolved oxygen deficit of the of the mixture of wastewater and river just downstream of the discharge point. All right, so take a couple minutes to look at that and solve that. And actually, I also meant to remind you there's last homework assignment is due Thursday. So today we'll talk through this problem, then deal with nutrient removal topics, biosolids, digesting topics, and that'll be it. So take a minute for this problem here. So the way I approached this problem was to take a look at, rather than solve everything in terms of the deficit, to take a look at, okay, well, what's the current dissolved oxygen, and then we can get to the final step and find the deficit given the saturation conditions. And that was from a lookup table. That was kind of the first thing I highlighted here. I forgot to talk about that, but we have a solubility lookup table for oxygen here. Depends on a few things. Temperature and chloride concentration are both important. We were not given any information about chloride, or maybe there was in the previous problem, so I just went ahead and highlighted the 0 mark. Of course, that's going to be different. This is at 20 degrees Celsius, 0 chloride. Of course, maybe the problem itself that we're looking at has some amount of chloride in the wastewater, so we have to calculate that. What's the combined chloride concentration given the wastewater and the river water? We could certainly do that and decide which one's closest to use that as an estimate. But here it's 9.09 milligrams per liter. We can see if we have a whole bunch of chloride, it could get down to 7.75 there. Okay, so anyhow, basically with these two rivers joining, and we want to know the new deficit there, I'm looking at the dissolved oxygen. So we've got the wastewater 2 milligrams per liter, the river water at 8.3. The combined flow is the 9.8 cubic meters per second. My mind really wanted to say meters per second squared there. So then, given a simple mass balance, the mixture, DO of the mixture times the flow rate of the mixture should be equal to the DO times the flow of the waste plus the DO times the flow of the river. So we can solve that and get a DO of the mixture for 7.59. And then that means our initial saturation, the initial deficit here is going to be that saturation value, 9.8, minus this 7.59, some milligrams per liter. And so that's going to give us, calculator, 2.21 milligrams per liter of dissolved oxygen. Okay, and in reality, probably a little less given the chloride. We probably would have some chloride there. Okay, makes sense? Yeah. Yeah, that should definitely have been 9.09. I'm sorry. 9.8 didn't make any sense. Thank you. So 1.5. So at least one of us is awake. That's good. All right. So then the problem continues and says, or I guess perhaps this is the next problem in line. Just below the discharge point, where continuous discharge of pollution mixes with the river, the BOD is 10.9, the DO is 7.6. The river and waste mixture has a temperature of 20 degrees Celsius, a deoxygenation rate constant of 0.2 per day, an average flow speed of 0.3 meters per second, an average depth of 3 meters. In other words, continuation of the previous problems. And part A says find the distance downstream at which the oxygen deficit is at a maximum. And part B, find the minimum value of dissolved oxygen. So I'm gonna get the our formula sheet and put that on the side for you to take a look at here. So A, we need the time and distance downstream where we find the oxygen deficit at a maximum. And B, we need to find that minimum value of dissolved oxygen that we we end up with. Going to pause for just a moment, and actually, what I'll do is I'll go ahead and see if I can cancel. I'm going to edit these slides for you. I'm going to bring them back over so you can actually watch. Start the problem.
inverse?
Okay, so that's a very good question. I was actually just thinking about that as I was working through that. So this KR here, um, bless you, is has to end up in per days because we have a KD in per days and just everything that's going to make the most sense. If you look at the units here, we've got the velocity or the speed rather of the river in a 1/2. So you're going to be left with something like meters per second to the 1/2. And then down here, it's going to be like meters, but to the 3/2. And so you're never going to have units that make sense. So as I stopped to think about it, I was like, well, if I just do the numbers here with meters per second and meters, we get 0.411, and that's relatively on par with this. And if we were to go back and check the table, that is in the range of the reaeration rate constants. It was like 0.1 was like a slow pond or something like that. 1 was a waterfall. So it's in the range that would make sense. The units can't make sense, and so I just took it as, well, this empirical formula must not be even matching, like, theoretically the units, right? They just threw it together and that works. And so I was going to make a note about that, so a great question. Normally I would say you have to follow the units, but I think that's, since it's just so empirical, they just, streams of this size, these dimensions, this speed, that's kind of what we get. So I was about to do it, that same thing, and then I was like, wait a second. Right. But it would actually be like seconds to the 1/2, so it's a very good thought. And we could take a look at the book and see if they explain that, which I bet they would. So let's go ahead and work through this. Basically, I'm going to be putting a lot of this into Excel. Did solve the KR, we talked about that. 0.411 is the value I got when I put in the numbers we had. If we had, let's say, kilometers and not meters, I think that would probably be an issue, and we'd want to convert to meters. So small caveat that we probably ought to go back and look at the book, and I say I ought to go back and look at the book to be sure that they say, okay, this must be meters and seconds or kilometers and days or something, and then we'll get a value. But this, like I said, appears reasonable to me. I think this is the way it ought to work, so we'll go with it for the moment. We also note that if KR is 0.411, that is not equal to KD, because KD is 0.2, and that means we are allowed to use this equation, right? So as long as those two aren't equal, we don't have a problem. So we're not going to use this equation today. So we've done that. This will get us the deficit, which will help us find the minimum value. So I'm just going to say this will be for part B. The critical time where that the stream is at most danger, let's say, that's this equation. We can get the distance as well from that. So this will be part A. Um, okay, so given that, the other information, like if we take a look at this, what we'll need, we need KR, we solved it. We needed KD, we're given it. We need the initial deficit, which we solved in the last problem. And we need the ultimate BOD. And that, we are given some information here that the BOD is 10.9 milligrams per liter. And that's not telling us that's the BOD5 that was measured there. That's just the BOD that is there. So I'm going to take that to mean that's our ultimate BOD. We're not given enough information really to do anything else with that. You know, if we had some information, if that was said, a 5-day BOD test told us it was that, and we were given some information about the BOD consumption rate, we could use the rate constant and use the equation for to find L naught and all that to derive that. But for now, since this is all we have, we're going to say L naught should be 10.9. Okay. So milligrams per BOD. All right, so then really we just need to put these numbers into Excel. That's my plan. Oops. Let's do this. All right. So we've got KR, KD, put L naught there. So this would just be an issue then of writing out this equation, which I'll do here. 1 over 1 minus KR minus KD times natural log of lots of stuff, KR over KD times 1 minus the DO initial. So the initial deficit we said was 1.5, right, from last problem. So I forgot to write that in here, but we'll go ahead and put it just manually. Times KR minus KD divided by KD times L naught. And that should give us a value in days. So 2.67 days. And then we can take that and say the distance, x, is going to be our speed times time. And that was 0.3 meters per second times 2.67 days. And then we can say I will need to convert, we can do times 86,400 seconds per day. We can also divide that by 1,000 for kilometers. So 69.2 kilometers. Okay, so the equations are involved, but as long as we get a good grasp of what pieces are going where, it really becomes a calculator entry sort of a deal. Okay, so then the last part, so that was part A. Part B then, I'm going to go ahead and separate this. Part B says find the minimum value of dissolved oxygen. That's going to be the deficit at time critical. So D, I could just do a subscript C, I suppose. And so really all we have to do is put in the time here. And since KR and KD are in per days, we'll know that's going to be the time in days there, 2.67. And so really it's just another matter of entering things that we already have. So we can do that. And I'm just going to make a note that the initial deficit, that was 1.5 milligrams per liter. Okay, so part B then, deficit at time critical is going to be equal to, you know what, I'm going to move this up here so it's easier. So deficit at time critical is going to be, we have KD times L naught. Divided by KR minus KD. Times E to the negative KD times the time we just solved, minus E to the negative KR times time. Okay, oh, added a 0. Oops. There we go. Okay. All that plus our initial deficit here times E to the negative KR times time. Okay. I need a bracket there. Bracket there. Okay. I think I missed a parenthesis, so I'm going to assume. Okay. So the value that returned was 7.77, and that looks to be a reasonable deficit. It's not above or below, but it's not above the saturation or below 0. So I'm going to trust that whatever I entered there is okay. So that's the deficit then. So that means DO minimum is going to be the saturation minus that. Saturation was 9.09. Okay, so in this case then, we had a biological oxygen demand of 10.9 milligrams per liter, and that deprived the water pretty significantly 2.5 days downstream. So the impact here is 70 kilometers away. We had a pretty nearly depleted oxygen supply in the water. So quite interesting if we consider those implications. So we'll say the deficit here was 7.77. I guess round up. And then the dissolved oxygen min 1.31. Okay. Does that make sense? Good. All right. So we spent a little while on that, which I hope was helpful. That gives a good idea of kind of how to approach these types of problems. There's a little bit I think that's covered in the homework with dealing with the rate at which you're consuming the BOD itself, the L naught and the L at some time t. So I think you'll have practice on that with the homework. All right. Okay, so I have some other slides and some videos, and perhaps I should just skim the slides and skip to the videos since we're low on time. I'll do a few slides and then might speed it up. Okay, so generally nutrient removal, what we're dealing with is we want to avoid the scenario we see here with an algae bloom. We could call it eutrophication, where we have some sort of a triggering event. Let's say we discharge lots of nutrients in a wastewater or agriculture runoff or something. We talked quite a bit about dissolved oxygen and biological oxygen demand, the issues therein. But what if we discharge water that has no BOD, but lots and lots of nutrients? Well, that can also be a problem, because if we trigger the growth of algae, which they basically eat CO2 during sunlight, if we grow a bunch of cells, a bunch of bacteria, whatever can grow based on all those nutrients, maybe they have some carbon source, some food sources, but they just didn't have the nitrogen or the phosphorus to really multiply. Well, then we discharge that and we have eutrophication. This is a big problem because at nighttime, when the cyanobacteria, the algae, all that, are no longer producing oxygen, or down below them where the sunlight can't reach, you have a bunch of organisms that are just doing respiration instead of photosynthesis. Likewise, when they start dying, the cells die and then they sink. There's a whole bunch of oxygen demand created by all those dead cells because there's lots of stuff. There's no oxygen being produced, especially in like a pond or some slow-moving water. The reaeration rate is pretty low. You're not getting oxygen down there, and so you can have significant fish kills and issues from what we call eutrophication. And if you ever see a pond or something maybe like in let's see, a small pond that kind of collects a lot of runoff from some agriculture land or something, it's not too uncommon to see it's bright green because that's just what's happening there. Okay, so that brings us back to that CNP ratio concept we talked about before, how important these macronutrients are for biological life. So the question then is, okay, how do we remove these things, and can we, rather than waste all of that, can we capture and retain that? Oops. Apparently I've got new gestures on this. Okay. All right. So regarding specifically the nitrogen cycle, One of the interesting things I like to talk about, and it kind of calls back to our BOD discussion downstream, is what happens when you release ammonia, some kind of organic form of nitrogen or ammonia, into water. And one of the things I like to highlight here is what happens when you set up a new aquarium, because one of the reasons I've always been interested in water treatment, things like that, is because I grew up with a couple of aquariums that I got to keep, and I'd go fishing in the creek behind my house and put whatever I could find in there. And I remember that whenever I would first start up a new aquarium, it was pretty common, and my dad had warned me about this, that whatever I put in there is probably going to die in about a week the first time. And so if you've ever kept an aquarium, you probably have faced a similar issue. And the thing is that when we add some form of ammonia, so let's say this is time 0 down here, of course, and we add a sudden input of ammonia, what's going to happen, or let's say we just add fish, right? And they're going to excrete ammonia, urea, things like that, especially if you feed them a lot. So if you do ever start an aquarium, put something small in it that you don't care too much about, or even just put some ammonia or whatever, some source of it, and just let it sit there for a couple weeks with aeration going and all that. Because what's going to happen is early on, there's not enough bacteria that can take it through the nitrogen cycle. And so you'll end up accumulating too much ammonia, which is toxic to fish. If not that, you might get too much nitrite, as we'll see. So if you have a sudden input, new fish, let's say you're going to have, or you could say new fish or some discharge of organic nitrogen. You'll have some formation of ammonia for a little bit, and then over time it'll be taken to 0. So maybe you don't have a whole lot of ammonia, but it keeps being excreted. So it might not be the worst of problems. But then ammonia is going to be converted to nitrite. Nitrite is also toxic to fish and other things. And what's going to happen is you'll get nitrite spiking and then eventually removed. And nitrite's going to be converted into nitrate, which is the most stable and the least toxic version. And so that will eventually take over as kind of the predominant nitrogen species. I think I had a better drawing last time I did this, so maybe I'll pull up this. So the point is, after some amount of time, maybe about 1 week for an aquarium or something, you will finally have some bacteria that are starting to take it through this cycle to make it happen. But in the scenario of a new aquarium, you probably were too excited, had too many fish, fed them too much, and now you had a lot of ammonia, which became a lot of nitrite, and it just hadn't been able to be converted yet. Later on, now that you have a nice colony of nitrogen processing bacteria in there, it'll be happening more rapidly and more smoothly. We'll see the same type of function if we discharge organic nitrogen or ammonia. It'll still be going through that cycle downstream. Of course, it'll probably look a little different because there will be the bacteria there, but it's still going to take some time, and we'll see this evolution of the nitrogen species. Okay, so that's kind of an interesting thing. And here I have a note that ammonia, anything above 0.5 milligrams per liter, is toxic. So if you just had the fish there and none of this stuff was happening and it just delayed for a very long time, you might just be increasing ammonia for quite some time before it significantly starts to be removed. Okay, another good strategy if you're happening to be wanting a new aquarium is you can take gravel that has been in a natural stream Of course, there's some risks there for if you're doing some sort of fancy tropical fish, you probably don't want to introduce potential pathogens, but I always like to get like the natural nearby fish. So not that would be a way to populate your aquarium with good bacteria kind of immediately. Okay, so we already talked a little bit about the nitrogen cycle when we dealt with it during VOD. So I'm going to skip ahead. Some of the processes we use for nitrogen removal in particular would be somewhat of a tertiary treatment, but we can, in some sense, connect this with our secondary treatment. So if we have a nitrogen removal process here, we have a primary sedimentation, so we've got primary treatment, and then normally here's our secondary treatment with an aeration chamber, but we could do something a little different. We could have this combined carbon oxidation and nitrification, so we're converting from NH3 type stuff to nitrates, and then we can do what we would call anoxic denitrification, so design a process to take NO3 to N2 gas, but we can't have oxygen around for that to happen because we need the bacteria to be using this nitrate as an oxygen supply. So that has to be a carefully controlled situation. And then do secondary sedimentation and continue as normal. So in this case, we've sort of inserted a step into the secondary treatment train to achieve that denitrification. This is just one example. There are many, but that's kind of a little feature of how you might do it. Here's another. This is the Bardenfo system, sequential use of wastewater carbon and endogenous carbon. So we have our raw wastewater. It's coming in. We first, or primary effluent. So we first do an anoxic denitrification. So before we even do anything, here's where we're trying to go from whatever nitrate exists into N2 gas. Once we get it into nitrogen gas, by the way, that's effectively removed. We consider that gone. It just goes to the atmosphere. After that, an aerobic combined oxygenation nitrification tank. So here we just started off by trying to remove any nitrate we have. Then we're going to convert into more nitrate, whatever happened to be digestible there, and then kind of sequence it back, right? So now we have anoxic denitrification again and another aeration tank. And so we're just kind of adding a couple layers here just to sequence it back and forth between the two, finishing with aerobic, which is probably has some advantages in terms of getting the water well oxygenated before we're about to discharge. So, that, and the caption here says this system for nitrogen removal can also be used for phosphorus removal with only slight modification. So perhaps this one also does a better job with phosphorus, given the back and forth. Okay, so there's some things like that. Phosphorus is an interesting one. If you remember from our CNP ratio discussion, the basis was phosphorus. We'd have one phosphorus, something like 10 to 15, 20 nitrogen, and like 100 carbon. So biological life comprises of mostly carbon. After that, about 5 times less nitrogen, something to that order, and then 10 to 20 times less than that is phosphorus. But it is essential. It's in that way, but we might call it a macronutrient, but it's the smallest of them, making up, like if you remember from biology, we have phospholipid membranes. That's very common in cells. It's kind of what we do, and obviously it includes phosphorus. Okay, so the phosphorus cycle is very different than the nitrogen cycle or the carbon cycle in that we don't have really an atmospheric component unless you're talking about bird poop. Birds actually do a significant amount of phosphorus cycling in that they excrete a lot, and sometimes that'll accumulate. There's like bird islands and things that is very rich. You might have heard of bat guano as a source of phosphorus. So we'll actually mine biological deposits in some cases for phosphorus, but otherwise it's pretty much mineral or kind of marine aqueous cycling. Okay, so it's a bit different. Several different process designs, um, making use of anaerobic, aerobic, and anoxic. Um, just a few different ones here. I'm not going to really spend too much time there. Okay, so another aspect we can do, aside from just simply, what can we do to cause the bacteria to process or to sequester them? Well, there's a question about what do we do now that we have all these bacteria in this solid form, all these nutrients in the bacterial form. Well, we can create biosolids, and so all that biological material, if we were just to landfill that, we're kind of wasting a lot of nutrients that we could use, because we're often taking nutrients, putting them in a bioavailable form, and applying them to our agriculture, right? And then when it comes to wastewater, we're just trying to get rid of them so we're not discharging them out into the water. So it's almost like we're fighting ourselves in a sense. So it would be nice if we could close that loop whenever possible. So biosolids, composting of biosolids is how we can go about doing that. What we need to do is to ensure safety in terms of pathogen reduction, and also we wouldn't apply to crops that we're going to be fresh produce, right? Even if we have a good pathogen reduction, we're still just not going to risk that. Contaminant containment. So if we suspect that there are still contaminants in our biosolids, which would be true to an extent, we don't want to apply them to places where that could get into direct exposure situations. So obviously there's some safety concerns with if we're not adequately treating the biosolids, which is basically the sludge turned into like a soil. That's kind of what we're talking about. Inadequate treatment or handling of them could be serious problems. Okay, so like I said, they are essentially fertilizer. It's a way to dispose, whether it's composting food waste or disposal of direct wastewater biomass. We can potentially recover biogas, so we can get usable methane from this type of process and recover a lot of the costs in doing all this associated with the wastewater treatment. Okay, so I'm going to breeze through a lot of this. Biosolids composting, it's essentially engineered compost. So if you've ever done some composting in your house or yard, you're just essentially trying to make nice, usable soil that can be a fertilizer for your plants and things like that. Here we're doing it on gross stuff, sewage, in a carefully controlled manner, but kind of for the same purposes, right? So once you apply them, it'll look something like this, where you're, if you were to apply them to a crop here, this might look something like this, where you're going to plow your fields, lay down a line of the biosolids, and that can be like a topsoil sort of situation. Now, I don't know if these are actually biosolids there, but kind of get the point. A lot of benefits to the soil, mostly pertaining to helping them to be a little to getting the soil to be a bit more aerated, better soil properties that are conducive to plant growth. Again, a lot like topsoil, right? We could look through this list, adding the nutrients. There's probably lots of micronutrients as well. Water holding capacity for soil, but also aeration drainage for clay soil. So it just kind of depends on what you're putting it in. Lots of potential benefits there. Disadvantages are going to be pretty straightforward. You've got odor at the composting site in particular. Once you apply them and they're aerated, it shouldn't smell too different than soil. Survival and presence of primary pathogens in the product is possible, so that's an obvious disadvantage. Like I said, we would not want to apply biosolids of this nature to anything that's direct human consumption. Dispersion of secondary pathogens, different fungi, particulate matter, allergens, some issues. You might have some lack of consistency in your product if you have, different things happening in your wastewater. That would also be true of the presence of heavy metals, which we're carefully controlling if we're applying to a field. Let's see. And then there's essentially two classes of biosolids that we consider. Class A being the most stringent, Class B being less stringent, and we absolutely guarantee that no public contact will exist, not just where we use it. So Class A, we meet really high standards. The public is allowed, we do allow for it to be used in places where public might contact this stuff or be around. Whereas Class B is like, nope, must be this far away from public roads or whatever else. Okay, and these these are classified based on how strict the processing is. So when you compost something, there's actually a lot of energy created by the biological activity, and that energy is released in the form of heat. So you've got these chemical and biochemical processes happening, and for the Class A, basically they say you have to let it get hot enough to achieve 55 degrees Celsius for at least 3 days. So that's actually pretty hot. Body temperature is 37 degrees Celsius, right? So this is like running a massive fever. This is probably, and we could look it up, but it's probably 120, 130 degrees Fahrenheit. That's hot. And so that's going to be stressing most pathogenic bacteria. I've worked with E. coli in the lab quite a bit. If they even touch 50 degrees Celsius for a moment, they're pretty much toast. They're not going to survive. They're going to be pretty unhappy. So getting it to that temperature is pretty significant. Keeping it there for 3 days, the way temperature acts is a lot like our chlorine type thing. The longer you keep it there, the more damage it does. So only certain organisms can resist that, and so we're going to be essentially growing those particular ones in these piles. There's also, it might be surprising that much heat can occur. Well, you can also get fires underground in landfills for the same reason. This type of thing can go out of control if you've got so much of the right chemistry happening. Okay, Class B then has a bit of a different classification, and actually I don't know, this windrow method, I guess there's two different Class A methods, right? The aerated static pile or in vessel, or this windrow where you have 55 degrees Celsius for at least 15 days with 5 turns. So one of them you're pushing air through it. The other is you just turn it every once in a while. All right, so Class B then is 40 degrees Celsius or higher for 5 days, during which temperature exceeds 55 degrees Celsius for at least 4 hours. So it has to reach that 55 Celsius mark, but it doesn't really have to stay there very long. So that's just not as strict. And so that's kind of the difference. Specifically for the pathogen removal is the issue there. Okay, so there's a maximum metal concentration in biosolids. This is relating back. This is actually a sub-program now of the NPDES system. A lot of states have it, a biosolids permitting process underneath that. So NPDES is primarily surface water discharge, but we needed some regulatory framework for biosolids, which is closely related to surface water discharge, but it's definitely not water. So it's just kind of, I guess, an odd placement, but that's how it went. So we can see that we have these ceiling concentrations, meaning we never want to allow the total milligrams of this particular contaminant per kilogram of biosolids. Like, we'll never be allowed to have more than this threshold for biosolids. And I think that then the resulting soil, there's two different standards. There's one, how much can we have in the actual biosolids, and then the second is what happens when we apply it and it mixes with the soil and the environment. And I think assessing both of those, then we have some ultimate limit of, okay, you can never apply more than such amount to a particular plot of land. Okay, just real quick, the process steps here. We typically dewater the stuff, and sometimes we'll bulk it, just adding some stuff like sawdust to add a little extra space, aerate it, let it be aerated a little easier. That's often something that we wanted to dispose of anyway, sawdust, corn husks, something like that. We want to then achieve that temperature between 55 and 65 Celsius, stabilize after that, letting it kind of reduce the temperature, do some drying if needed, and then sometimes you might separate back out that bulking agent, but usually not. Moisture content is kind of the critical aspect of all of this. We start with these very sludgy biosolids, so usually we have to dewater them a bit, but we still need them to be pretty moist for all this biological activity. Optimally, we have about 50 to 60% water in this, but enough, like plenty for biological activity, but not so much that it's actually mud, right? We actually do need air to get through. So this is a kind of a picture of what it might look like for this aerated static pile process. So we have all this sludge piled up and a blanket sort of thing put on top, and then we're pulling air through a vacuum here, out a little discharging. Here's where we get the smells coming out. So we have as much filtering that we can and preventing flies from getting in and all that. So air will travel essentially through here, in through here, and out. Of course, we're also going to collect a lot of juice, sludge juice, which we'd send to wastewater. And so you'll just essentially be operating these piles for, as we saw, numerous days, and then we will remove the blanket and then collect and discharge them. So it's like you get a series of piles and just let them run for a long time, and sequentially, every few days you'll take one out or whatever. There's also in-vessel composting systems that are a little bit more like a reactor itself, different designs, different ways to make sure you're getting plenty of oxygen and all that. Okay, so then at the end here, I've got 3 little videos. Don't have time for them all, but just kind of show you in case you're curious. One here is this one on biogas. It's a cartoonish thing, fun little kitschy music and funny pictures of bacteria and stuff. Pretty informative. A lot of these are kind of advertisement type things, right? So it's like they're telling you, whoever, I don't know who their intended audience is, maybe this is a sales pitch or something, but it's like, we'll play it for a moment here. So you get an idea.
Welcome to a virtual tour through one of BioConstruct's biogas plants. Controlled fermentation of biomass in biogas plants produces...
Okay, so that's all about biogas, and then so they've got essentially a kind of an animal, I think it's probably a pig farm or something, so probably concentrated animal feeding operation, and they're taking all this manure, creating biogas out of it, is kind of their concept there. So they're going through the technological stuff about that. We have a phosphorus removal thing. This is a shorter video, 3 minutes. Another advertisement sort of a situation. Oh no, never mind. This is just a fundamental on phosphorus removal. No, yeah, it was okay. So they're advertising this floating mixer thing. So they give a little bit of a 1-minute rundown on phosphorus removal, why it's important, and then they launch into this.
So let's get our removal on. Phosphorus can be removed from a lagoon by applying a precipitating agent like aluminum sulfate or ferric chloride. Once precipitated, the phosphorus harmlessly falls out of the water column and into the sludge sediments. Precipitant dispersal is a very hands-on and costly process requiring extensive labor, time, infrastructure, and accessory resources. In short, it can be spendy, spendy, spendy. This is where Medora's floating wastewater mixing equipment can make phosphorus removal a whole lot easier and more cost-effective. And it all starts with a floating wastewater mixer. The mixer is anchored using a single shore-to-shore tether cable which is able to span most lagoon dimensions. Once tethered, an injection hose is run from shore.
Okay, so they're advertising a cool little mixer thing for wastewater ponds, right? So it's fancy. They have some reasons. So it's a little technological overview. Last is another kind of a silly animated video on just a nitrogen cycle. So if you were more curious about that and wanted to see some cute animation of bacteria, nitrogen fixers and stuff, check that one out. But we kind of covered all that one already. All right, so I just wanted to show you what's there, and let you go. So any questions, concerns? All right, so we'll see you Thursday. We'll do the exam review, homework, go over the homework solutions. That'll be it. Have a good day.